You know when you're driving past a huge vineyard or maybe an orchard, and all the trees are planted in these perfect, neat rows? You get this really weird visual effect, right? You see these clear lines of trees, but as you move, your view shifts, and all of a sudden you can see way, way deep into the gaps between them. It's a super cool effect, and believe it or not, it opens up a whole field of mathematical puzzles called orchard problems.
So today we're going to tackle one of the simplest, but honestly one of the most mind-bending of these problems. Just imagine you're standing at the edge of a forest that goes on forever. I mean, an infinite forest. Is there any direction you can look where your line of sight just keeps going and going, or are you always eventually going to hit a tree?
Okay, so let's really dive into this. To even begin to answer a question like that, we first need to simplify this whole forest idea down to a nice, clean mathematical model.
So here are the rules of our game. Rule 1, we're standing right at the origin, point 0, on a graph. Rule 2, the forest of trees stretches out infinitely in front of us, filling up one whole quadrant of that graph. Rule 3, there's a tree planted at every single integer coordinate, basically at every single point where the grid lines cross. And Rule 4, and this is the absolute key to the whole thing, these trees have no thickness. They are just infinitely thin, perfect mathematical points.
Now, when you're faced with this infinite grid of trees, most people have the exact same gut reaction. Of course you'll hit a tree. I mean, even if you try to aim for a tiny gap, the forest goes on forever. Sooner or later, your line of sight has to hit something, right? It just feels like obvious common sense.
Well, that perfectly reasonable common sense intuition is about to run headfirst into a mathematical buzzsaw. Because the key to figuring this out isn't about how far you can see, but the precise direction you're looking.
And to define direction mathematically, we use a pretty simple concept you probably remember from school: the gradient, or the slope of a line. It's just the rise over the run, how far up you go for every step you take forward.
And this is where it gets really elegant. See, every single line of sight that actually hits a tree has a gradient that you can write as a simple fraction. For instance, if you look along a line that goes up 2 units for every 5 units it goes across, its gradient is 2 over 5. And that line is going to go on to hit the tree at coordinate 5, 2 perfectly. Every single tree corresponds to one of these fractional gradients.
So here's the crucial point. Any line of sight with a rational gradient, that's just a number that can be written as a fraction, is guaranteed to eventually hit a tree. But what about all the other numbers? Numbers like the square root of 2 or the most famous one, pi. These are irrational numbers. They can't be written down as a simple fraction. And if their gradient can't be a fraction, then by definition, a line of sight following that path can never hit a tree with integer coordinates. It will just slip through the gaps forever and ever.
So we did it. We found our gaps. There are infinite lines of sight that never hit a tree. But, that just raises an even bigger, crazier question. Which one is more common? Hitting a tree or slipping through a gap?
Okay, this is where our brains might start to melt just a little bit, because it turns out there are different sizes of infinity. I know, weird, right? The rational numbers, the ones that correspond to our trees, are what we call countably infinite. You could, at least in theory, start making a list of all of them, and if you had forever, every single one would eventually show up on that list. But the irrational numbers, our gaps, are uncountably infinite. It's like trying to list every grain of sand on Earth. You can't even start, because between any two you pick, there's always another one. There are infinitely more gaps than there are trees. And this all leads to a truly shocking conclusion. If you were to pick a direction completely at random, the mathematical probability of your line of sight having a rational gradient, and therefore hitting a tree, is 0. Not like close to 0. It is absolutely precisely 0. Just let that sink in for a second. You are standing in a forest with an infinite number of trees planted everywhere, and yet, mathematically speaking, you can't see any of them. The gaps are so much more numerous than the trees that the entire forest is, for all intents and purposes, invisible. It's basically all gaps.
Okay, that is just deeply weird. So let's try a new question to bring this whole paradox back to something a little more tangible. Let's forget about the infinite directions for a moment and just focus on the trees themselves. We know that some trees block our view of other trees, right? The tree at 2, 2 is obviously hidden behind the one at 1, 1. The one at 4, 2 is hidden behind the tree at 2, 1. So if you could pick any tree at random from this whole infinite forest, what's the probability that it's actually visible from where you're standing?
Well, the answer comes from another really beautiful piece of number theory.
A tree is visible only if its x and y coordinates are co-prime. Now, that's just a fancy way of saying they don't share any common factors other than the number 1. So, for example, the tree at 3, 5 is visible because 3 and 5 are co-prime. But the tree at 6, 3 is not visible because both 6 and 3 can be divided by 3, which means it's blocked by that much closer tree at 2, 1.
So the question really becomes, what's the probability that any two random integers are co-prime? And the answer, incredibly, is 6 divided by pi squared, which comes out to about 60.8%. And there it is again. Pi just shows up out of absolutely nowhere to give us this beautifully strange answer. So yeah, just over 60% of the trees in the forest are actually visible.
This all leads us to one last, really fascinating question. We know there are infinite gaps, but is there one single path, one specific direction that's the best path out? A route that stays as far away from every single tree as it possibly can?
It turns out there is. The line of sight that does the absolute best job of avoiding all the trees has a gradient equal to the golden ratio, often shown with the Greek letter phi. It's famous in art and nature, sure, but in math it's known as the most irrational number, which basically means it's the hardest number of all to get close to using a simple fraction. And that quality makes it the perfect tree dodger.
And here's one last beautiful, mind-blowing connection. If you look at which trees get the closest to this golden path without being hit, as you move out from where you're standing, you see they have very familiar coordinates. First, 1, 1, then 1, 2, then 2, 3, then 3, 5, 5, 8. Are you seeing it? Those are the Fibonacci numbers, hiding in plain sight right there in the structure of our invisible forest.
And that just leaves us with a final thought to chew on. We started with a really simple, intuitive question about looking through a forest, and somehow we ended up talking about different sizes of infinity, the number pi, the golden ratio, and the Fibonacci sequence. It just makes you wonder, right? What other deep, profound mathematical truths are hiding just beneath the surface of the world we see every day?